Okay, so this is AS1 Physics 1 Jun2005, and this is question 6 from that paper. And the first part of the question is, state how the principle of conservation of charge applies to currents at a junction in the circuit. Well, that's fairly straightforward because the sum of the currents into the junction, so the sum of into a junction is equal to the sum of the current leaving the junction. And remember, current is equal to charge per unit time, so that means that the charge per second going in is equal to the charge per second leaving. If we take a look at this, then we have 2 amps coming in, 3 amps coming out, 5 amps coming in. So in total we have 7 amps coming in, 3 amps going out, which means that we must have 4 amps going out at that point there. So the magnitude of the current is equal to 4 amps, and the direction is away from P. So 4 amps and away from P, as shown in the diagram here. We then have a fairly simple calculation involving resistors in series. So we have 6.2 shows a circuit in which resistors of resistance 500 and 100 connected in series, battery of EMF 12 volts. Battery has negligible internal resistance, okay, so we don't have to worry about any internal resistance. Connecting wires have negligible resistance also. And we're asked to calculate the current in the circuit. So if we come back up to the diagram, then what we know is that the total resistance is equal to 600 ohms because we have 500 and 100 in series, therefore it's just simply add those. We then have I is going to be equal to V divided by R, so that's equal to 12 divided by 600, so that means that I is equal to 0.02 amps. Therefore the current there is equal to 0.02 amps. Figure 6.3 then is an incomplete graph to show the voltage V at various points in that circuit. So we're starting at this point here, A, and then we're going around to B, through C, through D, and then back to E. So if we start here, A, and we have a current of 0.02, so that means we have a drop across here. So from A to B it stays constant, the voltage stays the same because we have negligible resistance in the wires, but from B to C we have a 10 volt drop, so it drops across there 10 volts. Then from C to D we have a further 2 volts drop, and then it remains constant throughout. So if we take a look at the graph, this is the graph that we have here. So from A to B it remained constant, but then from B to C it dropped down, and the voltage drops down like so. Then from C to D it drops a further 200, stays constant across here. And then from here, this is where E to A, that's back across the battery, that's where it now gains the EMF that it had lost around the circuit inside the battery, and so it goes up like so. So we have a complete graph traveling along the wire, no PD, through the first resistor 500 ohms, big drop in PD of 10 volts, through the next resistor, slightly less drop, 2 volts, then it stays constant because between D and E is travelling through the wires, and then from E to A through the battery it gains its PD again.